Okay, so we are going to look at the third case of partial fractions. So in this case, we have where q of x, which is the denominator, it has irreducible quadratic factor. So what does it mean to be irreducible? That they cannot be further factored. So for example, an expression like this, x square plus a square, is so we can't factor it as what we say in real numbers. So if you have, for example, x squared plus 1 cannot be factored, so we say it is an irreducible quadratic factor. Or something like x squared plus x plus 2. So you cannot factor it in real numbers. In other words, when you try to find the values of x, you end up getting complex values or complex numbers. So you do not get real numbers. So then we say this is irreducible. So looking at this example, you notice first thing that the degree of the numerator is smaller than the degree of the denominator. So we can think about partial fractions. So how do we see that what type or case we should be considering? The first thing is to factor out the denominator. Now notice, even if the numerator can be factored, do not factor it. We do not worry about the numerator as long as we know it is a polynomial. So we will only worry about the denominator. So in this case, when we factor the denominator, we end up getting x times x squared plus 4, and x squared plus 4 cannot be factored further. So we will be using this third case of the rational functions. And what is the third case? Well, when you have a quadratic factor, again going back, when you have the linear factor, we saw that on the top we just put a constant. Why? Because constant is 1 degree less or 1 degree smaller than the linear. In the same way, if we have a quadratic factor, or quadratic polynomial, then the polynomial which is 1 degree less than the quadratic will be a linear polynomial. So that we put a linear expression or a linear polynomial on top of our quadratic factor instead of putting just a constant. Now it could be that in our answer we only have, we only get it in the form like 2 over x squared plus 4 or 1 over x squared plus 4. Well, then automatically when you find the values, you can end up getting b equal to 0. Sometimes it might happen, but not always. So we will write it as, whenever you have a quadratic factor, you will put a linear factor on top, whether ax plus b or bx plus c or cx plus d, or depending on how many of those coefficients you have already used. The rest of the procedure is similar. So the difference in all these different cases is setting up. The first step, setting up, how will you set up your partial fractions, and then the procedure is very, very similar. So we will multiply by LCM on both sides, and we see that we end up getting this equation, which is what you get. And now we do the same thing by setting x is equal to 0. Why? Because 0 is one of the number which is not in the domain. So we set x is equal to 0, and we end up getting one of our coefficients. But now notice we don't have any other number which is not in the domain. So now we just pick up numbers, whatever is you think is easier. Now, can you pick x is equal to 2? Yes, of course. Can you pick x is equal to minus 7? Yes. Minus 5? Yes. Plus 7 or plus 3 or yes, whatever number you want to pick, you may pick. But since it's easier to deal with ones and negative ones, so we will start with that. Now, if we need it, we can go to the next 2, negative 2, and so on. But if this is sufficient to find our values, then that's all we will do. So we set x is equal to 1, and by doing that we see that we do not get a single those coefficients, but we get an equation of two of these, b and c. And already we are using the value for a in here, because a is something we already found. So when we got this equation in b plus c equal to 0, well, we now can say that c is equal to minus b, but we do not have a value for c and b. So we need to pick another value of x, for example, -1, and plug in, and we get a second equation in b and c. So I'm calling them equation 1 and equation 2. So by putting a number and then circling, that is the equation numbers. And now I write 1 plus 2. So what does that mean? This means adding equations 1 and 2. So instead of writing it in words, adding equations 1 and 2, I am using their symbols. So this means equation 1 plus equation 2. So it gives us, and if you recall, how do we add equations? The left-hand side in the left-hand side and the right-hand side in the right-hand side. So when we add these two equations, c and c will get cancelled, and we end up getting 2 equals 2b, which gives us b equal to 1. And again, from equation 1, you can see that c is equal to minus b, which gives us c equal to -1. So now we have our expression, our given fraction as a sum of two partial fractions, in which one of the denominator has a quadratic factor and one has a linear factor. So that now we can go back and say, okay, integral of our given will be equal to integral of this plus the integral of that. Now the first one is easy to integrate, just ln of absolute value of x. But the second one, again, now we have to do further steps. So we notice that if we have just x over x squared plus 4, we can use substitution and do it. And so we split it and we write it as x over x squared plus 4 minus 1 over x squared plus 4. So the first one I have shown here, for this one, we can use the substitution. U is equal to x squared plus 4, so that du is 2x plus dx, so that this expression becomes 1/2 du over u, or 1/2 ln of u, or 1/2 ln of x squared plus 4. Now notice here, I didn't put absolute values here, and which is okay. Why? Because remember, even if you write it like this, it's not wrong, it's perfectly fine. But since x squared plus 4 is never going to be never going to be negative, so we don't need bars around here. We can put parentheses. In the same way, for the second integral, which is this one, we, as I explained in the beginning of the 7.4 section, an expression like this is actually can be becomes tangent inverse of x over 2 with 1/2 in the front. So if you remember it directly, you can write. Otherwise, you can use this substitution. X is equal to 2 tangent theta, and then go over, and then you end up getting this. So then we can now write that our given integral is equal to ln of absolute value of x plus 1/2 ln of x squared plus 4 minus 1/2 tangent inverse of x over 2 plus k. Why? Again, because c was used in the coefficient, so don't put c here. Now note here that something I want to mention, that the tangent inverse of x over 2 is the same thing as arc tangent of x over 2. So you can also write it like this. But tangent inverse of x over 2 is not 1 over tangent of x over 2. This is something we learn when in pre-calculus, when we are define the inverse trig functions. And so this is a mistake which often students make, and which is something should be emphasized over and over again, that these inverse notations are not powers.